Welcome back, everyone, to the Deep Dive. Ready to explore something we all use every day but never really think about.
What's that?
Units and measurement.
Yeah. Sounds pretty basic, right?
Well, maybe at first glance, but believe me, there's a whole lot more to it. It gets really fascinating the deeper you go.
Oh, I bet. Units and measurements, they're like, the foundation of how we understand the world, right? Science, engineering, even just everyday life. We need a way to quantify things.
Exactly. But I'll admit, I usually just take units for granted, like meters, liters, grams, just use them without thinking about where they came from.
Yeah, it's easy to forget that it wasn't always like this. I mean, for centuries, different parts of the world had totally different systems. Imagine, like, trying to build a bridge if one side's using feet and the other's using cubits or
Oh,
something.
wow, yeah. Total chaos.
Exactly. That's why the SI system, the International System of Units, was such a game changer. Finally, everyone's speaking the same language.
Just kind of like the Esperanto of measurement.
Yeah, I like that. It's all built on these 7 base units. Meter for length, kilogram for mass, second for time, ampere for electric current, Kelvin for temperature, mole for amount of substance, and candela for luminous intensity.
Okay, so those are like our fundamental building blocks.
Exactly. And from those, we can derive all these other units, like for speed or force.
Like pushing a shopping cart, there's a force there, right? And it can be measured in newtons.
Absolutely. Physics in action, even at the grocery store.
I never thought of it like that. So how do they even decide on these base units in the first place? Like what makes a meter a meter?
That's a great question. The definitions have actually evolved over time. You know, the meter used to be defined as like a fraction of the Earth's circumference.
Really?
Yeah, but as technology improved, they needed something more precise.
So what is it now?
Well, now it's based on the speed of light in a vacuum.
Wow. So a meter is the distance light travels in a vacuum in, what, some tiny fraction of a second?
Exactly. 1,299,792,458 of a second, to be precise. That level of precision is super important, especially for things like GPS or scientific experiments.
Yeah, I guess a rough estimate wouldn't cut it for those things.
Yeah.
Okay, so we've got these precisely defined base units. We can use them to make all sorts of other units. But how do we make sure our measurements are accurate? That's where significant figures come in, right?
You got it. Significant figures are all about conveying how precise a measurement is.
Okay. I remember struggling with those in school. Why are all those rules about trailing zeros so important? It always seems so nitpicky.
Well, those digits can make a big difference depending on what you're measuring. Like,
Yeah.
imagine following a recipe. A tiny difference in the amount of salt can change the whole dish.
Okay, yeah, I get that. But what about in science? Is it really that critical?
Oh, absolutely. Significant figures tell us how much confidence we should have in a measurement. They reflect the limits of our instruments and the uncertainty inherent in any measurement.
So it's not just about the number itself, but also understanding how reliable that number is.
Exactly. Significant figures are all about communicating that reliability.
Okay, I'm starting to see the light here. Maybe we could do a quick refresher on the rules for figuring out significant figures.
Sure. So all non-zero digits are significant, right? And any zeros between non-zero digits are also significant.
So like 203 would have 3 significant figures.
Right. Now, trailing zeros, those are only significant if they come after a decimal point. Like 3.500 has 4 significant figures, but 3,500 only has 2.
So the decimal point is like a signal that those zeros are important.
Exactly. And remember, when you're doing calculations, your final answer should have the same number of significant figures as the least precise measurement you used.
Got it. So we're being honest about the level of precision, not making our results seem more accurate than they really are.
Exactly. Scientific integrity.
This has been a great overview of units and measurement so far. We talked about the importance of standardized units, like those in the SI system, and how significant figures help us communicate measurements accurately. But there's another tool, right? Dimensional analysis.
Oh, yeah, absolutely. Dimensional analysis. It might sound intimidating, but it's actually pretty intuitive and super helpful. Almost feels like magic once you get the hang of it.
Okay, I'm intrigued. Measurement magic. I'm ready for it.
It's all about using the dimensions of quantities like length, mass, time to check if our equations make sense and even to discover new relationships.
Well, let's dive into that then. Sounds fascinating.
So dimensional analysis, it's like a secret weapon for physicists.
Oh, really? Like how?
Well, it lets us double-check our equations, make sure they're, legit.
Okay.
And sometimes even find new relationships between things, physical quantities.
That sounds pretty powerful. Can you give us an example?
Absolutely. Let's take the equation for distance traveled under constant acceleration. It's x equals x0 plus VOT plus 12 at 2. Remember that one from physics class?
Oh, vaguely. Something about starting position, velocity, time, and acceleration, right?
Yep. Now, let's think about the dimensions of each part. X and x0 are both distances, so their dimension is length. We'll call that L.
Okay, length, L.
V0, the initial velocity, that's length per time, or LT, time t is just t. And acceleration, a, that's length per time squared, or LT2.
So we're breaking the equation down into its basic dimensions.
Exactly, like
Yeah.
translating it into a different language. Now, let's substitute those dimensions into the equation. We get L plus LTT plus 12, LTT2, see what happens.
Yeah, the TS cancel out in the second term, and the T2s in the third. So we end up with L plus L plus L.
Exactly. Everything on the right side boils down to length, which matches the left side. That means our equation is dimensionally consistent. Good sign.
So if the dimensions didn't match up, we'd know something was off.
You got it. It's a great way to catch errors. Now, remember I said dimensional analysis can help us find new relationships, too.
Yeah, that's the part I'm really curious about.
Okay, imagine a simple pendulum swinging back and forth. What do you think the period of the swing depends on? You know, the time it takes for one complete swing.
Well, the length of the pendulum, for sure. A longer one would swing slower, right?
Right. And also the mass of the bob and gravity.
Okay, makes sense.
So we can write this relationship as T equals KLX gyms, where T is the period, L is length, G is gravity, M is mass, and K is just a constant we'll ignore for now. Those exponents, X, Y, and Z, are what we need to figure out.
Right, those are the unknowns.
Now let's write out the dimensions. T equals LX, LT2Y, MSE. To get the time dimension on both sides to match, what does Y have to be?
Well, we need negative to Y is 1. So Y has to be negative 12.
Perfect. Now for length, we need X plus Y equals 0. And since we know Y is negative 12, X must be 12.
Okay, and there's no mass dimension on the left, so Z must be 0.
Exactly. So our formula becomes T LTLL, 12, G net is just 12, 0. And anything to the power 0 is just 1.
So it simplifies to T AF LS KRT LG. Well, we just figured out the formula for the period of a pendulum just by looking at the dimensions.
That's the power of dimensional analysis. Pretty cool, right? It's like it reveals these hidden connections.
It really does feel like magic.
It's like having a secret code book for the universe. Dimensional analysis helps us understand the underlying rules of physics.
This has been amazing. We've talked about standardized units, significant figures, now dimensional analysis. What else is there to explore in the world of units and measurement? So much to think about. Units and measurement, who knew there was so much to it?
Right, and we're not even done yet. There's this whole other side to it, how units shape the way we see the world.
What do you mean?
Well, think about it. The units we use, they kind of define how we think about things. Like, if we only measured time in years, our whole view of history would be different than if we used nanoseconds.
Yeah, I guess that's true. Different scales for different perspectives.
Exactly, and that can impact all sorts of things, from scientific discoveries to everyday decisions.
So the units we use, they're like a lens we see reality through.
Yeah, that's a great way to put it. And it's important to be aware of that lens, understand its limitations.
Makes me wonder, are there any units that are particularly, I don't know, misleading, easy to misinterpret?
Oh, definitely. Think about calories. The ones we see on food labels, those are actually kilocalories.
Oh, right. It's easy to forget that.
Yeah, it can be confusing if you're not careful. So it's not just about the number itself, but also the unit it's in.
That's a good point. Pay attention to the units. This whole deep dive has been eye-opening. Units and measurement, it's so much more than I ever realized.
Right. It's like there's always more to learn, even about things we think we know.
So what's the biggest takeaway you want our listeners to leave with?
I'd say remember that units and measurements, they're not just numbers. They're powerful tools that shape how we understand the world.
They shape our understanding, influence our choices, even how we see reality.
Exactly. The more we know about them, the better equipped we are to, navigate this world that's so driven by data and science.
Well said. This has been a fantastic deep dive. Thanks for joining us.
My pleasure.
And to all our listeners, stay curious. There's always something new to discover. Until next time, the Deep Dive signing off.